Hello and welcome everyone. My name is Hannah Mason and I'm a technical editor at Composites World. I want to thank you for joining us today for this webinar titled Sustainability in Bio-Based Products in the Composites Industry, brought to you by Composites World and presented by Entropy Resins. Our presenter today is Desi Bonatau, Global Sales Manager at Entropy Resins. Desi is a seasoned materials science professional and co-founder of Entropy Resins, a company that pioneered the introduction of bio-based epoxy formulations for composite applications. In 2018, Goujon Brothers Inc. acquired Entropy Resins, and Desi currently serves as Global Sales Manager. With a diverse background in developing and commercializing advanced material systems, his expertise spans sectors ranging from semiconductors to polymers. So he's here today to talk about sustainability and new products. His presentation will be followed by a question and answer session. So attendees, if you have a question, you can type it in at any time during the webinar in the Q&A field that you see on your screen. You'll also see next to the Q&A tab, a chat tab that you can use to chat among the attendees, fellow attendees, and a handouts tab with materials available to download from Entropy Resins. So before we get started, as a last note for me, this webinar is being recorded and when complete will be made available to you via email from Composites World. So if you miss anything, you'll be able to watch it back later. All right, without further ado, welcome Desi. It's all yours.
Thank you, Hannah. Welcome everyone, and thank you for joining this webinar. Again, my name is Desi Bonatau, currently the Global Sales Manager for Entropy Resins within the Goujon Brothers family of epoxy brands, which also includes West System, which I'm sure a lot of people are familiar with, and ProSet. Entropy was founded in 2010 with a focus on bringing sustainable epoxy formulations to the composites industry. And we joined Goujon, as Hannah said, in 2018 and have continued to grow this mission through that partnership. So as a quick agenda for this webinar, I think whenever I'm introducing our brand, I think it's always important to start with definitions. What exactly do we mean by sustainability and what makes our products sustainable? I think our approach has always been from the perspective of scientists and engineers. And we believe, just like any mechanical property or processing parameter, sustainability can be measured and represented quantitatively. So I'll start with how we do that, then jump into how we interpret that within our product line. And I'll close with introducing some new products that we're launching this year. So if we start at the highest level, I think despite a lot of progress many companies and industries have made providing sustainable solutions to their customers, sustainability can be something that's pretty nebulous. And so I think it's always important to have some sort of guiding ethos when you build out a sustainability plan. Ours is pretty simple. It's something we call people, planet, and industry. On the planet side, again, something pretty simple. There just needs to be some net measurable benefit for the environment through the use of our products. Unfortunately, this is where a lot of companies can stray kind of into greenwashing land. But again, our approach is to try to do this quantitatively and focus on simple concepts like minimizing waste or using less energy or resources to produce our products. On the people side, we are dealing with chemicals, so it can be a lot more complicated. But product safety for users is always number one on our list. Who and where we buy raw materials is another important factor. And then giving back, both monetarily or through knowledge sharing, is something that we always try to be cognizant of. And lastly, industry. We have to understand who our customers are and provide value to them. I think that's important for any business, no matter what you're trying to sell. Ultimately, in our minds, this is beneficial to the industry by providing products that customers want to buy, but also new pathways for growth. We've also recently seen a lot of regulatory and legislative requirements around the composites industry and around the chemical industry. And we also feel like we can help the industry solve these problems in unique ways. So if we drill down a little further and focus on the planet side of this ethos, kind of the next level where we try to define is how we plan for sustainability in our product design. For us, that planning process always starts with raw materials. Our main goal is to replace as much of the petroleum-based raw materials that are conventionally used in this industry with something that we call rapidly renewable biological sources, or plants. That doesn't necessarily mean that we're trying to grow plants and turn them into plastics. I think in our analysis, there isn't much of a net benefit for the environment with these types of direct conversions. I think there's been a lot of examples out there in the industry ranging from like ethanol fuels and other types of plastics that are doing direct conversions where there really isn't a net benefit due to the amount of energy required to grow plants and turn them into plastics. So much like the existing plastics industry, we're trying to source our raw materials from waste streams or co-products of other industrial relevant bio-based feedstocks. The next step, design and manufacturing, is something that pretty much all formulating businesses need to be good at to be successful. And that's taking this collection of raw materials and designing and manufacturing products that meet the market requirements. I think another guiding ethos for us that helps us through this design manufacturing phase is that, at the end of the day, no one's going to care how eco-friendly a product is if it doesn't work, right? And no matter how beneficial your product is for the environment, if people don't use it, you don't capture that benefit, right? So in the case of the composites industry, the definition of working is usually based on some performance parameter. So our products always need to meet or exceed the performance of our competitors, whether they're bio-based or not. Cost is also an important parameter, and I think that's something that's often lost in this idea of sustainability, is that we need to be cost competitive, right? And that could be as simple as lowering kind of a bill of materials, but it could also be based on things like reducing your manufacturing cost and reducing the kind of total cost of ownership of that product or process. Lastly, end of life. What happens to the product when it reaches the end of its usable life? I bet there's been a couple Composites World webinars about this topic alone. I think it's something that's the industry is becoming more and more aware of. Today, Entropy does not provide a biodegradable or recyclable solution, but it's something that we're working on and something that we feel is also very important in this planning for sustainability and product design. Hopefully in the future we can talk about it. Maybe it'll be the topic of our next webinar. So with the decision making in our product design process defined, we'll drill down a bit even further down, and that's looking at the various phases of a product's life cycle. More specifically, we want to quantify all the inputs and outputs that go into the phases of a product life cycle. What we actually start to build out is kind of an equation, right? Where you have inputs like raw materials and energy that go into raw materials or manufacturing processes, as well as outputs such as waste for each of these phases. Oops. And ultimately, this equation is what's commonly referred to as a product life cycle analysis, or LCA. It's an evaluation of the potential environmental impacts of a product through the compilation of these inputs and outputs of its life cycle. And this ultimately is the evaluation that we use to quantitatively measure our product's net benefit or not for the environment. I think one thing you always got to be cognizant of is especially if you're doing some quantitative study like this, the answer could be that it isn't beneficial for the environment. But that's part of this whole process is trying to understand that and be able to make decisions based on that. So now that we've defined kind of our thought processes behind the how and why we get to the LCA, I think I'm going to dive now into the specifics on how one actually conducts an LCA. And there are four distinct phases in building an LCA. You start with your goal and scope, right? What do you want to study, and what parameters do you want to put around that study? The next step is something called an inventory analysis. And this is really the meat of the work, where you actually need to go and collect the actual data of the inputs and outputs of each phase of your product's life cycle. This data can come from a lot of different sources, but the main sources will be primary data from your actual processes and secondary data, typically in the form of something called inventory data that's available from third-party sources. And a lot of the times, this is where your raw material data will come from. Once all this data is collected, you'll plug this into an algorithm, usually a software tool, which will then calculate or assess the impact of your products in various impact categories. Those impact categories can be wide-ranging, everything from effects on the climate, effects on people, effects on the land. I think this is another area that people really need to understand what they want to study in order to really pick the right categories. Lastly, there's the interpretation phase, and this is where you define what it all means, right? Also, I'll give a brief overview of the first two phases specific to what we've done here in Entropy, but then I'm going to jump into our products and to help give some context of the assessment and interpretation phases. So goal and scope for our Entropy Resins LCA. As a company, we wanted to understand the environmental impacts of our products and opportunities where we could reduce them in order to quantify the net environmental benefit of our products. On the scope side, so in order to do that, we needed to be able to create an LCA model for our bio-based liquid epoxy resin products. But we also needed to create a model for an industry standard petroleum version that we could compare our version to. The next phase, the inventory analysis phase. I'll say this was not an easy process, right? I think this took the better part of 2 to 3 years to complete fully. Collecting data, especially environmentally related data out of an industry that is notoriously sheepish about divulging this type of information, took a ton of effort. But with the help of a few key raw material providers and a lot of work from our LCA practitioners who partnered with us, we were able to piece together a complete data set for not just our product, but for also an industry standard version of epoxy. For our study, ultimately, we stopped at, our LCA stopped at what we call a gate. And essentially, this is a point at which our product leaves our facility. I think in that decision, the assumption was that creating further value from a sustainability standpoint was really up to the customer. Again, and today we're just kind of looking at something that we call, cradle to gate versus cradle to grave. End of life, again, is something that's really important and something that we're working on and the industry is working on. But at least for the sake of this discussion today, we're just going to be talking about cradle, essentially sourcing all our raw materials to the gate of us delivering our product out of our facility. So I'll touch briefly on the assessment phase here, but then I'm going to jump into the products to give it more context. But these were all the environmental impact categories we keyed in on: human health, ecosystems, resources, climate change, cumulative energy demand, and water use. So we were able to pick those 6 categories. When we plug in our data into the software program, it gives us back information based on these 6 categories. For brevity's sake, I think we'll focus in on the bottom 3, which are the ones that our customers are very keyed in on, and that's climate change, energy demand, and lastly, water use. As Hannah mentioned, though, I think our full LCA report is available for download as part of this webinar. So not quite sure how that works, but it should be available if you want to dive kind of deeper into some of these other impact categories, or at least think about or learn about more about the process that we've used to develop our LCA. So now I'm going to transition a little bit into our products, and again, we'll circle back to those last two phases of an LCA and kind of give you examples of how we apply them in the context of our products. So again, Entropy Resins, we are an epoxy formulator focused on creating performance bio-based products. Again, I think the performance aspect that is always important to us, that have some certifiable bio-based content and reduced environmental impact as measured by LCA. We participate in something called the USDA Biopreferred Labeling Program, where we have our bio-based contents of our products tested by a third party and verified using an ASTM standard test. The USDA program is a labeling program that helps them find products for consumers that use some minimum amount of bio-based content. And this can range from a lot of things. From if you go into the grocery store, you'll probably see like detergents, other cleaning products are all using this label to identify themselves as a bio-based product. Our product was the first epoxy product to be labeled in this program, and we actually helped define the labeling program requirements for the adhesive category, which today stands at a minimum of 25% bio-based content. This is our standard product line, which consists of room temperature epoxy cure systems for both laminating and casting applications. We also have an elevated cure line that's primarily used for compression molding. As you can see, all of our products meet and are certified by the USDA labeling program. So again, jumping back into kind of the LCA and how we apply that to our products, and we'll focus again on the bottom three impact categories, starting with climate change. So climate change is measured by kilograms of CO2 equivalents, and we saw a 14% drop in this category for our bio-based product versus the industry standard petroleum-based product. I think the first question I get from everybody is, what in the hell is a kilogram of CO2 equivalents? Again, I think the interpretation phase of the LCA is very important, and this is how we take something as obscure as kilograms of CO2 equivalents and making it relatable to customers, or better yet, our customers, because again, often we're a raw material that goes into a product that then is sold to a consumer. So we need to be able to kind of transition a bunch of levels and explain kind of what the LCA means. So again, looking at this climate change impact category, so what we try to do is take this unit of measure and represent it as something familiar to people kind of in their daily lives. In the case of kilograms of CO2 equivalents, we converted that into the amount of pollution created per mile of your average combustion engine car. So when we look at it this way, with 1 gallon of resin, we're able to save 10 miles driven by a standard car. So if you use 1 gallon of our bio-based product versus the industry standard, that gallon saves you those 10 miles of a driven car, which individually probably doesn't sound like a lot, but for a lot of industrially scaled processes that use hundreds, if not thousands of gallons of epoxy per year, this number can really add up. So moving to our next category, cumulative energy demand. This is how much energy is required to make the product. Again, we're seeing the savings in the low teens of our product compared to the industry standard as measured by megajoules. And then converting this megajoule figure into something that we feel is more relatable to individual consumers. 1 gallon of resin, we can save something up to 1,300 smartphone charges, which is something that always impresses my kids, whose worst fear is their iPhone or iPad running out of juice. 13,000 charges is a lot of TikToking. So. And then lastly, water use. Again, a similar savings of 16% per cubic meter, as measured by cubic meters. And that equates to 85 16-ounce water bottles per gallon of epoxy. Again, something that individually may not seem dramatic, but if you scale that across a large epoxy user, it really starts to add up fast. So I think, Hannah, I'm not sure if that kind of concludes kind of the LCA portion of the discussion. I think we're going to transition into the product section quickly, and then I think we can field questions from the audience. How's that sound?
Sounds good.
Okay. So we'd like to talk today about a new product that we're introducing to the industry, and we call it the bioinfusion system. It's a resin system that's designed specifically for resin infusion or RTM processes that are commonly used in the composites manufacturing industry. We have 2 flavors. There's a QC system that's tinted to ensure proper mixing, so yellow and blue makes green. And then we also have a clear UV resistance system for cosmetic parts that require low yellowing. If you're familiar with Goujon's ProSet line, there's a very popular system called INF. Our Biobased system is designed off of that, and a lot of the years of experience that went into that system, we've applied here for the bioinfusion system. Where do we see this product fitting into the market? I think historically, the traditional markets that Entropy and our Biobased have been used have been the sporting goods industry, specifically things like action sports, so like surfing, skiing, snowboarding, where our lamination and kind of press molding systems have fit those manufacturing processes. With the bioinfusion, we hope to expand to a more standard composite industry, namely things like built environments or architecture and transportation. While we do see potential adoption in traditional markets like marine, we see greater synergies in kind of emerging fields that combine concepts like electrification or autonomous driving. I live in California in Silicon Valley, so I kind of have to believe that flying cars will be a reality one day. But I do also think that things like sustainability really start to fit with the ethos of some of these emerging applications for composites, like electrification and autonomous driving. So I think with that, I'll kind of leave you guys with these takeaways, and we can start to see if we can answer some questions that people have.
Okay, sounds good. Well, thanks so much for the presentation. That was great. So like Desi said, we'll kind of launch into some questions here. We'll start with a few that have come in already. And of course, attendees, if you have questions, now's the time. Use the Q&A tab on your screen. So we'll start with this one. What is the maximum bio content an epoxy can reach? Or can you kind of speak about the bio content?
Sure. I mean, so we're going to jump into a little chemistry here, but epoxy is usually built from epichlorohydrin and bisphenol A. I think most commonly that there's a bisphenol on one end and the epichlorohydrin on one end. Epichlorohydrin can be sourced 100% bio-based. The other side of it today cannot. So if you're making a conventional epoxy molecule, the maximum is somewhere around 28%. Now, I think there's been a lot of work around replacing, the bisphenol A with something that could be 100% bio-based. We've played a lot with those molecules. There are a lot of good potential applications for those in adhesives or things that don't require the structure of an epoxy and a composite matrix. I think that's kind of the holy grail, though, is how do you replace, bisphenol A or bisphenol F with something that can be bio-based and still maintain the mechanical properties of that molecule. Again, so because of those limitations today, I think most of the time what you'll see is somewhere around that 28% number for just an epoxy molecule.
Okay. Related to this, and you've kind of addressed this a little bit, but this person asks, 32% bio content is related to resin. What about hardener? Do you have a bio version?
We do employ bio-based materials in the hardeners. I think from a system perspective, we do have systems. If you include the bio-based content in the hardener, we can get up to somewhere around 40 to 50%. The USDA program used to be designed to measure a system bio-based content. They switched to doing individual products. And so again, what you see today is just us certifying the resin component. I think just off the top of my head, probably the highest bio-based content hardener we have is probably somewhere around the 40 to 50% range. But again, because we're only certifying one side of it, we're just certifying the epoxy side. But yes, there are bio-based hardeners. The industry is also working on that. And I've seen some interesting new molecules out there where, such as, very commonly used hardeners like IPD, where you can get them to be bio-based. So that's coming for sure.
Okay. When you say bio-based content, what does that mean? You mentioned a little bit of kind of the raw material supply, I guess.
Yeah. So the way that technically petroleum is bio-based, right? I think, it just comes from biological sources that were around millions of years ago, right? I think the main way that we define it, and, I use the term rapidly renewable, but the way that, the ASTM test works is they call something called, there's modern carbon and there's dinosaur carbon, right? And that's really how we define bio-based, right? So modern carbon is carbon that's essentially been in our environment for, as long as humans have been around versus dinosaurs, right? And that's kind of primarily what we're talking about is sourcing biological material that has been in our environment. And don't want to get too complicated with this, but like the issue with around petroleum is those were carbon resources that were around millions of years ago. We're pulling them up and we're reintroducing them into our environment. That's causing this imbalance, right? So when we talk about bio-based materials, what we're really focusing on is bio-based materials that are modern or that have been in our existing environment.
Okay. Is there a fire retardant version on the horizon?
We do have fire retardant systems. So I think I talked a little bit about our standard products. One thing that we do is do custom formulation for customers with larger applications. I think we have customers that range from buying, a few quarts of resin all the way up to container loads. We do have an FR system was specifically designed for one customer doing one application. I think, the hard part with FR is there's so many different versions of FR. And I do know that there's some products that are out there that, are class A or rated in some very generic way. But I think for us, FR is we try to treat that as a custom product. So if that's something that you're interested in, definitely, we can, I guess, probably need to drop our contact information so that people can contact us about understanding more about what we can do from an FR perspective.
Next question. I can't remember the exact value that you mentioned here, but they said that TG is quite low. Why is that?
Well, and I'm not sure which product they're referring to, but the TG. So for our room temperature cure systems, I think TG and getting a good room temperature cure are kind of opposing forces, right? I think, if you can do post cures, if you can do elevated cures, then it's easier to gain TG, and you can give up things like room temperature cure. So for all our kind of room temperature cure systems, those are purposely set low in order for us to get good room temperature cure properties. Now, that if you're looking for something higher TG with a room temperature cure, I think that's the realm that's hard to satisfy. We can do higher TG systems, and if you look at the bioinfusion system, I think that you'll see that TG to be closer to what you would expect from more standard composite products in the composites industry, or resins in the composite industry. But again, that's requiring a post cure. So I think it really depends on your process and what you can do, and that helps us with gaining things like TG.
Okay. Next question.
But I think generally speaking, I don't think our systems have a lower TG than other conventional systems, apples to apples. I think we can always attain similar TGs with our bio-based raw materials than are attained by standard systems.
Okay. The next question is, do you have any comments about using natural fibers like flax with bioresins?
Yeah, we've done a lot of that work. I think I'm an engineer, so the first thing I'll say is getting a natural fiber to work as a replacement for something like fiberglass or carbon fiber is extremely hard. I think if people are trying to replace things like fiberglass or carbon fiber with natural fibers, that's a very tough engineering prospect, which isn't to say that there aren't good applications for it. I think just like any specialty fiber, thermoplastics, Kevlar, whatever they are, you just need to be cognizant of how to use them, with and take what they're good at and apply it into your laminate structure. Things that we've been very successful with natural fibers is damping, mixing, having hybrids with carbon and natural fibers for damping characteristics. Cosmetics, obviously, I think people are really interested in the look of natural fibers. We've made natural fiber pre-pregs that people have used in things like musical instruments, bike parts. So you just kind of have to make sure that you're not you're achieving your engineering tasks or goals when you're adding things like natural fibers.
Okay. Do you, if for anybody that has a question about this or other things, do you have a slide with your contact information or for Entropy that you can put up?
Oh yeah, sorry. There we go.
Okay. Let's see. Moving on to the next question here. Is there a bio-based resin specific for medical or pharma products?
Oh yeah, FDA approval. We don't have one. I think there's been a couple applications that we've looked at. I'm not exactly sure what pharma or applications you're talking about, but we've looked at FDA approval for things like potable water or food contact. and we've done projects related to that. I think that in and of itself, the materials can be certified for those applications. I think the way that we've always treated it is we don't necessarily have our products FDA certified. But we can help customers get their products certified. So I think one easy example to describe was we worked with a customer to make an engineered surface for food service. So these are going in restaurants, and we were able to help them get. In this case, it was more NSF than FDA, but it helped them get NSF approval so that they could certify their products for food service use.
Okay. The next question has two parts, and you addressed the first part kind of a little bit already in the TG question. But how do the mechanical properties of the bioresin system compare with traditional epoxy systems? That's the first part. And do you have an aerospace grade bioresin system on your roadmap?
Yeah, I mean, again, I think if we can't meet those mechanical properties, we wouldn't exist. I think I'll probably answer this with a kind of chemistry description of what we try to do. I think there's two things that we're commonly doing. We're creating what we call chemical offsets, meaning the molecule itself is analogous to its petroleum counterpart. In that case, there's absolutely no performance drop, right? We're just making the exact same molecule. And if I put those two molecules in front of a chemist, they wouldn't be able to differentiate them from each other. We also do functional offsets. So in some cases, we're taking not exactly the same molecule, but a bio-based version of a molecule that's very similar. In which case there might be some performance drop, but I think this is where the formulation comes into play. We try to find combinations of those molecules in order to not just meet, but sometimes in some cases improve the mechanical properties. So again, I think first and foremost, if we went to a customer and said, well, here's a bio-based product, but the performance is 10% less, they're not going to care. So we always need to be cognizant of that. I don't think we ever will try to put a product out there that showed some inferior mechanical property. I forget the second part of that.
Do you have an aerospace grade on your roadmap?
So the bioinfusion system, I wouldn't necessarily say we're focusing it on aerospace, but we're definitely focusing it on transportation applications. And I was kind of joking about flying cars, but those are the types of applications that we see this product being used in. Structural components for again, we're working on things like drones or marine applications. I think while I'm not quite sure if we'll ever get aerospace ratings on these products, I think they can definitely be applied into anything that's flying in the air.
Okay. We have some more questions about different kind of end market applications. We have a diverse audience today from different end markets. So you've obviously talked about several of these, but this person asks specific to automotive, which you mentioned flying cars. For automotive industry, could the bioresin be used for EV battery casings?
Yeah, absolutely. I think I'm not quite sure what the material systems that go into that. It's probably some carbon fiber or something like that. But I think again, anything there where you're currently using epoxy resins and fibers, it's definitely applicable.
Okay. And then another question about marine, which you mentioned, but they specifically ask, is it suitable for marine industry where products are long-term submerged in seawater, such as for components on yachts?
Yeah, I think again, what we're trying to do is make epoxy systems that work like any epoxy system that you would normally be using. I think in this case, or at least for the infusion system, there's the ProSet infusion system. We have a ton of experience with in marine. I think if it's probably the most widely used epoxy infusion system in the marine industry today. We take all that knowledge and we apply it to what we're doing at Entropy for the bio-based side. And again, if we have a drop in performance from a conventional system, to us it's not a product, right? So our bio-based infusion system can be used in marine very similarly to any ProSet or GURD or whatever the system that you're using for infusion. Now, epoxy in general does have some requirements to be used in those applications, and those aren't products that we sell, but these are you start to get into the coatings and above and below the waterline coatings, and those are all those things still apply to our bioinfusion system, but they apply to all epoxy systems.
Okay. What R&D challenges remain for these materials to be widely adapted commercially?
R&D challenges. Yeah, I mean, I think the toolbox that we have can be smaller, right? I think, if any standard epoxy formulator has thousands and thousands of products that they can choose from, we don't. So it is a much more challenging formulation effort a lot of the time. I think somebody asked this question about hardeners. I do think hardeners, while there's been a lot of work put into creating bio-based epoxy molecules, there has not been a lot of effort put into creating bio-based hardener molecules. And if we want to continue to increase the bio-based content of the overall systems, I think that's probably where the most opportunity lies in making these systems, higher bio-based content and having more tools to enable formulators to create different products.
Okay. Next question is, what is your opinion on the mass balance approach?
Yeah, I mean, the mass balance approach is mostly around carbon footprinting. I think that you can use LCA models, or you can tweak your LCA models around mass balance approach. I think for us, we were more focused on the impact assessment of via climate change of the kilograms per CO2 equivalent, because for us it was a much more tangible unit of measure for our customers. But yeah, I mean, I think you can use the mass balance approach in a very similar way to quantify carbon footprinting.
Okay. Do you have any products in development or available suitable for 3D printing applications?
3D printing. So most of the, I think, 3D printing thermoset resins, I believe, are kind of UV cure systems. Epoxy in general doesn't have a lot of free radical curing, or at least free radical curing materials for things like composite matrices. We actually have not really worked on that at all. So today I do know of bio-based UV cure epoxy acrylate systems. Those are mostly used for like coatings and paints. But that industry is pretty active in trying to identify some new sustainable materials. So I think if you're interested in that, I would probably go in a direction of checking out some of the epoxy UV cure acrylates that are used in those applications.
Okay. Does Entropy produce epoxy or hardeners for hot melt systems?
We have done that, and we are working on that. So I'm assuming they're meaning hot melt pre-preg systems. So we do have, in our toolbox, we do have the ability to create higher molecular rate epoxy systems that would go into hot melts. And again, we've done that in the past. We made natural fiber pre-pregs, and we're working on, we're always constantly working on creating new formulations for the pre-preg industry.
Okay.
It's something that's not standard in our product line. Again, something if they email us, we can kind of hear more about what they need and see if it's something that we can supply for them. But yes, we've done hot melts in the past.
Okay. We have a couple more questions just about how these products compare to a conventional epoxy system. One is back to kind of mechanical performance. Is there any comparison in terms of the strength or performance of a product, such as the structure made of conventional epoxy versus bio-based epoxy? Is it lesser or higher, and in what extent?
Yeah, I mean, again, I think if we ever try to do an apples to apples comparisons with something, we always want to be as good or better, right? I think if we can't do that as a formulator, whether it's bio-based or not doesn't really matter, right? I think customers in this industry aren't going to accept inferior mechanical properties. Now, there are cases where we'll purposely design systems for with various mechanical properties for various reasons, but that's always to improve it. And I think probably one example I'll use is our compression molding systems, right? We've worked extensively in the ski and snowboard industry. We have a lot of major brands that use our products today. Things that we found is for high flex, high fatigue products, elongation of a material system is extremely important. And so when we go and design our compression molding system, while if you look at a TDS, it might look like it has a lower modulus. That's actually by design, because what we're trying to do is improve elongation, and that ultimately helps improve the strength or the the lifetime of a product like a ski or snowboard that's a very high flex, high fatigue part. So I think in general we would never compromise the mechanical property. If you see it in a TDS or something like that, that's usually for a reason, right? I think we're trying to achieve some mechanical performance that will ultimately benefit the end user, the end part.
Okay. Another comparison question: how does bioresin compare in cost to traditional epoxies?
Yeah, I mean, it is more expensive. I think that again, it's more about in this case, it's more about just the amount of material that's produced versus conventional material, as well as the certification and the work that goes into identifying those raw material sources and making sure that you're actually producing what you say you're producing. It's not crazy more expensive. I think it's for the way that we always try to describe it to our customers is if we're adding a penny to your part, we need to be able to turn that penny into $1 at the end user. I think if I had to give you a number, I mean, we're somewhere anywhere from 10 to 20% more expensive in most cases. But, I think our goal is to deliver value through, these LCA models, certification, being able to communicate these things to your customers so that, that whatever that percentage is, ultimately is value gained, at the end customer.
Yeah. One question says, if you're in the case of, competing products from different companies that both quote, say 30% bio content, how could someone kind of know the difference and which one to choose? Or what advice would you have, I guess?
Yeah, I mean, testing. I mean, again, I'm an engineer at heart, so and I think I've said this a lot during this webinar. It's while we are about delivering sustainable solutions, these products need to work right for your application, and the best way to understand that is testing. I think just like whether if you're comparing, I think we do this a lot, right? Where they're comparing our bio-based system versus a conventional system or another bio-based system. I don't really see that as a difference, right? I always see that it's like we're comparing our products versus other products, right? And from a usability, processing, mechanical, whatever perspective you're looking at it, we have to win, right? I'm not saying that ultimately the sustainability thing is just for free, but I think the way that I always, when I'm ever talking to our sales guys, it's like the sustainability concept might open the door for us, but we need to close because we're good engineers or we understand the product or the process the best.
Yeah. Okay. A question about balsa wood core specifically, I guess, that this person is using is in an application using balsa wood core, would any primer be necessary to reduce resin absorption by the balsa wood?
That I'm not entirely sure of. I would think whatever people are doing with standard resins, you should do. I mean, that does sound like a good way to prevent absorption in the wood, so long as whatever primer you're putting on there adheres to the resin and to the wood, because obviously you're creating a new interface in there. I know that the epoxy will stick to the balsa extremely well. Now, how deep it absorbs and how much weight that adds, I'm not entirely sure. But I think probably if you're adding that primer layer, it would just need to make sure that that interface is as good as the epoxy to the balsa normally is. And of course, here comes the guy with the blower right in front of my office. So.
No worries. Right, so we've got there you go. We've got two more quick questions here, and then we'll wrap up the webinar. What do you think of using epoxy resin for a composite used in water filtration?
Yeah, I mean, either way, you'd probably need to get some sort of certification around use in potable water. Maybe if it's wastewater, it probably doesn't matter. Epoxy is a great material to be used as a coating in aqueous situations, whether it's water or other types of chemicals. It's commonly used for that. And again, I think our materials behave very similar to any epoxy that would be used in that type of application.
Okay. And last question that we have time for here, are you focusing, it's Entropy Resins, focusing on any non-epoxy bio-based thermoset resins in development?
Non-bio-based thermosets. Goujon does have
non-epoxy. I'm sorry, I misspoke the question. Perhaps non-epoxy thermoset resin developments that are bio-based.
We've looked at a lot of other types of thermosets. Mm-hmm. I think we would always probably stay out of anything that's styrenated. I think that's obviously our ethos of what we're trying to do from a sustainability standpoint. Doesn't really align with things like styrene. So I would say that no on that part. But for anything that's 100% solids we've looked at, I think urethanes are an interesting area that we've looked at. Don't have anything today, but I think those, I would say anything that's not solvent-based or styrenated is interesting to us from a bio-based materials perspective. Okay.
I think that's all the questions that we've got time for at the moment. So we've come to the end of the webinar here. Thank you so much, Desi, for your presentation. We appreciate it.
Yeah, and thank you everyone for attending. And again, my contact information is there, and would love to hear more of your questions, and hopefully we can answer them for you.
Yeah, sounds good. Thanks also to our attendees for joining us today. We appreciate you being here and hope you'll join us again for the next Composites World webinar. For more information on that, please visit compositesworld.com and have a good day, everybody.
Thank you.